Okay, let's start. Do we have half of the class at least is here? So let's start. Now, let me give you the register, please. Thank you. Um, Last week we didn't finish class 6. We couldn't finish class 6. The last question. I think we will do bits and pieces of it. Class 6, 3, question 3. And we will move on to class 7 quickly. So let's look at class 6, question 3. There are two methods, but we'll use the easiest one. It's autoregressive process, so substitution method works as well, but we don't use it. Class 6. Question 3a. It says, suppose that YT follows a stationary AR1 process. YT follows this process. Let me tilt down the door, guys. Yeah, well, class 6, question 3. So first, what we're given that expected value of YT is some mu y, not given, but that's what we are going to use. Oh, actually, it's given. Sorry, or is it not? It's not. Sorry. We will be using that. Expected value of ut is 0, and variance of ut is 9. Some constant. A. Compute the mean and variance of yt. That's the standard procedure that we did last time. Remember? And its expected value of 2.5 plus 0.7 times expected value of yt minus 1 plus the expected value of ut. This will give you mu y equals, this is 0 constant, yeah? Sorry, I'll be quick on this. This is 7 mu y plus, we know the expected value of u is 0, so all we get is, sorry, did I put 0 here? This is 2.5. Expected value of a constant is a constant, so this is 2.5. And solving for mu y, you should get 2.5 over 1 minus 0.7, which gives us 8.3. Keep this in mind, we'll use it later for other calculations. Next, the variance of yt is basically variance of all these three. This, we don't have the variance for constant, so it just drops out. And expanding the square bracket here gives us variance of yt minus 1 plus 2 covariance of 0.7 yt minus 1 and ut, and plus variance of ut, var ut, and that will give us 0.7 squared times if you remember variance, we usually denote this sigma u squared plus sigma y squared this time, and this is sigma u squared, right? And we are given this, that the variance of ut is 9, so you'll use that information. Nine. From there we have 9 over 1 minus 0.7 squared, which is 17.6. Done. That's A. Quickly compute the first autocovariance for YT now, if you finish. So these two results will be used in the next solution. Right, let's go on to B now. Page. I'm not doing. I'm not explaining a few points. I mean lots of points that we just went through because we've done this before. It's just to provide you with solutions. I'll try to be quick. So we need to go to class 7 as well. Now, first, autocovariance. If you remember from last week, okay, covariance of, basically it's covariance of, it's not Y, covariance of YT with its first lag. If it's second autocovariance, then it will be covariance between YT and YT minus 2. Third autocovariance, then it's third lag, and so on and so forth. Now we are given the values for YT, and they are 2.5 plus 0.7 YT minus 1 plus UT, and this YT is minus 1 is from before. Now take the covariance of each term with the other variable, which is YT minus 1 now, will be 2.5 YT minus 1 plus covariance between the second term and YT minus 1 plus covariance UT and YT minus 1. Now, what's the covariance between the 2.5 and YT minus 1? 2.5 obviously is a constant and random variable, do not covary, do not correlate, so 0. Plus, how about this? What am I going to do with 0.7? Right, so it's going to go out and leave us with covariance between YT minus 1 and YT minus 1 plus, how about this last term, covariance between UT and UT minus 1? They are IID, so 0 given in the equation, yeah, and I'm not correlated between, yeah, and otherwise you'll have this sort of omitted variable bias, the case where UT contains something that correlates with YT minus 1 with the independent variable. Now we'll have now this times this thing here. What is this thing? Covariance YT minus 1 and YT minus 1. Last week we discussed this. Variance, and we know what the variance is, 17.6, which gives us 12.35. Done. Now, question here, next question is about second autocovariance or autocorrelation, isn't it? No, it's not the one. Sorry, it says first two apparently. So we'll do only first one, and I will do C now. I'll skip and do C only. You can do the second autocovariance, which will have now covariance of yt and yt minus 2. I won't do that. It's the same procedure, yeah? I'll just go to C and I do first autocorrelation. The second autocorrelation is for you to do at home. You have the solution already, I guess, isn't it? Right, so autocorrelation now. First autocorrelation, C. Correlation yt and yt minus 1 is basically the covariance that we have just done over variance yt times variance yt minus 1. Sorry, it's not enough. Okay. This, so the top is this, and this here is this. So we get correlation coefficient of 0.7. Now D. Suppose that yt, y big T is equal to 1 over 2.3. Compute yt plus 1 next period. Given that we know this period, then it is expected value of estimated equation. So this would be 2.5 plus 0.7 yt. Plug that in. Gives us 7, 4, 11. Done. It's the conditional expectation. So given that we know the past values, future value would be 74.11. Class 7 now, quickly. If you do not have questions, class 7 page, erase everything. Class 7. Okay. 1A. So we given this index of production IP in monthly frequency. The period is given, sample period. Sorry, guys. Class 7. So we have a guy forecasting IP growth rates using this formula. Times 12 times 100. Is this correct? Annualizing the monthly rates. Now, let's go back to the original formula. This involves ln, so it's approximation to growth rate. This would be the actual growth rate formula. Now, usually, if we are annualizing, we would take the growth rate and raise it to power of 12 if it's monthly, 4 if it's quarterly. So this time it's monthly, so raise it to power 2, 12, and this would give us the annual rate, annualized value. Now take logs of this, take ln, take log, so you'll get ln IPT over IPT minus 1, 12 minus 0. This ln1 is 0, right? Then we will get 12 times ln IPT over IPT minus 1. Because we're interested in percentage rates, times it by 100 gives us 1200 ln IPT over IPT minus 1. This would be the solution. So he's done it the right way. Yes, it's correct, and I just explained you why it's correct. The way you derive the 1200 times ln IPT over IPT. -22 I think we need to rush now. Right, next. Shh, guys, you're disturbing the students. Right, so we need more space. We'll go to next blank page. 1B. 1B. Now we are given this model, AR4 model. In autoregressive models, the dependent variable is regressed on its lags, and lag order is in the bracket. So if you have AR4, it's basically YT being regressed on its 4 lags, past lags. So you have 4 lags, basically, up to 4 lags, right? Now, suppose this AR4 model, use this AR4 model to forecast the value of YT in January 2001. Okay, using the following values of IP. We are given the following values of IP. I will have to copy these. That's easiest, I think I can do now. So 2007, month 7, 2000, month 8, 2000, month 9, 2010, 11, 12, and the one that I have to forecast is 1. And we are given IPTs 147.6, 148.6, 148.9, 148.66, and 148.2. Last one is 147.3. Now, if you want to use the formula, the estimated equation to forecast, we need to convert these IPTs into growth rates using the formula YT equal to ln formula, right? And that was YT was equal to 12 times 100 times ln IPT over IPT minus 1. So we'll have to use this formula to calculate each of these. Now, we know values, so we can plug them into this. I'll do the first one and then give you the rest as a solution. Now, to get the growth rate from month 7 into 8, 12 times 100 ln IPT in this case is 148.6, IPT minus 1 is 147.6, and that is, there is some typo here, it's 7.73, but it's actually 8 point something if you calculated it. It's 8 point something, but I'll leave it as it is in the solution, 7.73. Now next one is calculated in the same fashion, so it's this values here. Minus 2.52, so there's a decline. decrease in the growth rate. So negative growth rate, not a decline, sorry. And we need to forecast this one, this bit here. And we'll use this equation that we are given. We are given that is this plus 3 times negative 7.36 plus 0.123 times negative 3.67 plus 0.068 times negative 3.52 plus 0.001 times 2.6. So I'm using the values that we just calculated, these values plugged in to the formula minus 1.58. So this is minus 1.58, this value here. Next is C. You can stop me if you have any questions. So what this guy did now is he was worried about seasonal fluctuations. As such, he decided to do this. Augment the model with 12th lag. So beta 5 is now YT minus 12. And the question is this important? Is this useful in the model? Individually, alone, on its own. That's test of significance, basically. And we usually do t-test for test of significance. And the formula is beta 5 hat over beta is standard error of beta 5 hat. And that is minus 0.054 over 0.053. That gives us minus 9. Now, the UT is missing, guys. Sorry, there's UT. Next, at 5% significance level, our critical value is 1.96. And absolute value of our t-stat is much smaller than 1.96. So null hypothesis that we have was this, right? I didn't state it at the beginning. Hopefully you knew what it is. It was. So fail to reject. H null. Done. Fail to reject H null. Okay, next. D. Now the person here, usually when you're dealing with time series data, goodness of fit, for goodness of fit, obviously you have to look at R squared, but for parsimony, for the best model, you have to look at some sort of information criterion or criteria if you have more than one. And they are BICs and AICs, Bayesian information criterion and Archaic information criteria. And now this guy is looking at it now, and he's worried about lag length. He's worried that he's got so many lags in AR4, so he needs to figure out what the parsimonious model is. For that reason, he calculates 6 models: AR1, 2, 3, 6, 4, 5, 6, and he needs to pick the best model. For that purpose, he calculates AIC and BICs for each of these, which means 6 times 2, so it's 12 AICs and BICs here. Now this is going to take long time to do this one by one, but I'll do first one and then last one. AR1 and AR6 BICs. Yeah, I'll calculate the BIC for first model and the last model, and I'll give you the final solution right away. Right. So it's just to demonstrate and show you how it's done, but I'll give you in the end the solution as well. Right. What is the formula for BIC? It's in your lecture notes. ln SSR P, P being the lag length, T plus P plus 1 times ln T over T. AIC P is ln the same as before, it's just the second term is different. Now, the person, this researcher estimated AR1, which is this model, and wanted to know if it is parsimonious, if the lag length AR1 is basically the good model. Now for that we will calculate BIC 1 ln the SSR for one lag, the sum of squared residuals for one lag is, if you look at the table, is 29175, right? Over T. So what is T here, guys? What's this T? Value for this T. Value for the T term. Number of observations, isn't it? How many observations are there? How many years included in the data? 1960 to 2000 is 41 years, isn't it? Times it by 12 because we're dealing with monthly data. So that gives us 492 observations. Plus P is 1, so people 1 plus 1 times ln 492 over 492. And it turns out it's actually 1. This is our BIC for the first model, and you calculate for the rest. And we jump to BIC 6. This is just to demonstrate the calculation, but we don't need to calculate anything between them. It takes time, so we don't have much of it, so we don't need to calculate. You get the solution in the end. I mean, it will be revealed later. So P plus 1 is now 6 plus 1 ln 492 over 492. That's equal to 4.1409. Now you do the same thing for AIC, just calculate AIC 6 for 6 different models. The last one here, guys, this one is for this model. So it's this model here, last one. You calculate BIC for the last, yeah. Yeah. Ah, sorry, did I copy it? Yeah, I did copy. It's 29175, it's wrong. It's 28317. 28317. Thank you. So eraser, small one. It's the SSR from model 6. Yeah, thank you. Done. And I'll give you a solution. It turns out if you do each of the remaining AICs and BICs for AR1 to AR6, according to BIC, the best model is AR2. According to AIC, that's for from BIC. From AIC, it's AR3. Now, how do we decide whether this is AR2, AR1, AR6, or whatever it is in this case? What decision rule? What's the decision rule? So you have 6 different BICs for each of the models, and it shows that AR2 is the best model. But how did we decide? How did this guy decide if whether this AR2 is better or not, best or not? Look at your lecture notes. It should say that smallest BIC or smallest AIC of all the AR models is the most parsimonious model. So, we just calculated BIC1 and BIC6. Between them, there are 4 more models for BIC2, BIC3 to 4, 5. Yeah, we skipped them, but it looks like AR2 is the best model with the smallest BIC, Bayesian information criterion. Smallest of all the BICs and AICs should give you the best model. However, BICs and AICs do not give you the final result. They usually conflict each other. Like in this case, BIC tells us we have to add 2 lags. AIC tells us you have to add 3 lags because it says AR3 is the best model. Now, final model has to be chosen based on economic theory now. It's fine if you go with BIC result. It's also fine if you go with AIC result. But you have to justify it using economic theory now. If both of them would agree that AR2 is best model in this case, both of them are saying, that will be fine. But now in this case, it's more conflicting. I mean, I was confused myself when I was doing my master's because in time to use econometrics, we had to do to find most parsimonious model, and AIC and BICs give us different models. One showing AR12, another showing AR10. And we didn't know which one to choose at the time. So we had to look at theory, and it's 12 months, so maybe there are some seasonal fluctuations, so we included AR12. But in fact, it is better to have the shortest lag model, the model with the lag or the smallest, usually, for the parsimony, for its parsimony, sorry. So we go on to the next now, if you do not have questions. I hope you understood all this that we just discussed. It's just time consuming to calculate all of the BICs and AICs. Right, next. Eraser, clear. So for this next exercise, exercise 2, this guy calculated this model, so I'll have to rewrite it to just explain you and give you intuition. Now this is, read the question please. I'm trying to copy the one from before. So he augmented the original model. This is 4. He augmented the original model with change in RT being interest rate, and it's 4 lags. Now the question is, the Grange causality F statistic on the 4 lags of change in RT is 2.35. So let's put this down as well. F stat is 2.35. Now we're dealing with Grange causality here. What's the hypothesis, null hypothesis for Grange causality test? Yeah. Of which one? These. Yeah. These were original coefficients, right? Original model. So he added change in RTs and tried to. Now, why do we do Grand causality here usually? Exactly. Grand causality deals with whether added or whether some sort of set of legs are useful in predicting the dependent variable. In this case, this research is interested in if changes in RT and its legs are good predictors of YT being the growth rate of IP, yeah, industrial production. So null hypothesis in that case would be beta 5 equals beta 6 equals beta 7 equals beta 8 all equals 0. An alternative that, sorry, rather than rewriting it, not H null, I think that's easier. Not H null, so that would be not equal, yeah? So we're looking at these last added coefficient, terms, the legs, and trying to test whether they need to be there or not in the model. Now we give an F statistic for this hypothesis. Question is, should we reject the null hypothesis or fail to reject? What should we do? Well, we need now F critical. How do we calculate F critical? Or how do you locate it from the F table? Anyone? How many degrees of freedom are there in F tests? So we need to calculate degrees of freedom 1, which is usually Q restrictions, yeah? We have 4 restrictions, in other words, 4 coefficients being equal to 0, right? 4. Degrees of freedom 2 is usually, this is time series, so T minus K minus 1. This usually is N minus K, but because time series, we have T observations 4, 9, 2 minus K variables 8, so we have 4 and 4, 8 minus 1. And if you look up this, the value for this degrees of freedom, given this degrees of freedom, this can be written as F for infinity, F for comma infinity. The reason for infinity is because in the table we have the values for only up to 120 and the rest is shown as infinity. So that's why we have the infinity here. You should get 2.372, something like this. So go to table, column number 4, because we have 4 restrictions. Go down along the rows, across the rows, sorry. At the bottom is this value, 2.372 for alpha equal to 5%. Decision time. What do we do? Reject, accept, not accept, fail to reject. This is F critical and this is our rejection region. And our F stat is in the acceptance region. So we fail to reject. H null. Now, question. What does it mean if we fail to reject the null hypothesis? In this context, what's the decision? Or what's the meaning of this fail to reject thing? Anyone? I didn't get it, sorry. It doesn't help. Or it does. It does. But what is null hypothesis? It says it doesn't, and we didn't reject it, so it shouldn't then, yeah? So it doesn't help predict growth rates of industrial production. So interest rates, changes in interest rates and its lags do not help predict growth rates of industrial production. Right. Next. Next, guy, what this guy did is now he ran the model but with a different dependent variable. If you read the question, it says, now he's trying to see if IP is a good predictor of change in RT. Yeah? So this is the dependent variable now. Change in RT. Have a look, guys. Take a look at the new model. Now, null hypothesis this time is that beta 1, beta 2, all equal to 0. Alternatively, not H null. And he has the F stat 2.87, and we have the critical value for the same degrees of freedom. Decision. What's the decision here, guys? Given the F statistic and critical value that we have at hand. Decision? Now we reject the null hypothesis, right? So we reject this null hypothesis that the IP is not cannot be used to predict RT. We reject it now. So it's an important term in the model. So we have to retain the lags of YT as, in other words, growth rates of industrial production grandly causes change in interest rate. That's the sort of economic conclusion based on theory. Not based on theory, it's just to give it a context, I should say. So we reject the null. And growth rates of IP are good predictors of growth rates of IP, and its lags is a good predictor of change in interest rate. Done. Well, this is again for 5% level significance. Yeah, we just looked it up. Hopefully you looked it up, not me. I didn't have the table, so you can check this. Next is now question 3A. Suppose that change in RT follows change in YT follows AR1 model, AR1 process of this type, and show that YT follows an AR2. So now we have to show that levels YT, not change in, this is change here. This is change, sorry. So we have to show that YT follows an AR2 model. Now we have to look at the basic definition of change in YT, which is YT minus 1, right? And change in not RT, I keep going back to RT for some reason. It's this thing here is equal to YT minus 1 minus YT minus 2. Now substitute change in yt with this term and change in yt minus 1 with this term basically, and you will have this following expression. No worries. And solve for yt. And collecting the terms with common factors gives us solution. That's the solution. You can call this some sort of gamma if you want. B just says what are the, B just asks what the coefficient estimates are, or coefficients are. So for intercept, coefficient is beta 0, coefficient of yt minus 1 is just gamma now, and coefficient of second lag is beta 1. So they are two different, these are different obviously. This is 1 plus some constant beta 1. That's answer to B as well. So just to identify the coefficients. So yt is a function of beta 0, beta 1 plus 1, and beta 1. Right? That's a solution to C. If I just, maybe we don't need B, yeah? Intercept coefficient is beta 0. Coefficient of yt minus 1 is beta 1 minus 1, sorry, plus 1. And coefficient of yt minus 2 is minus beta 1. So we have two lags of yt, and yt is an AR2 process. Number 4 is an eViews exercise, and I don't have eViews now in this computer, so I'll have to switch the computers. But I don't know if I have enough time for this. 7 minutes. So let's wrap it up here then.